Hello, everyone. I would say good evening, but I'm aware where most of you are, it's probably not evening. So my name's Mythreyi, and I'm a PhD student at the Queensland University of Technology, and I would like to present some of the work that my co-authors and I have done around evaluation of explainable methods for predictive process analytics. So firstly, what is predictive process analytics? It's essentially a way to identify how some future state of a running business process. So for example, how it's going to end, or how long it's going to take before it ends. And the thing with predictive process analytics is it often uses very sophisticated machine learning and AI algorithms to create its predictions. The problem with these algorithms tends to be that they are often what we call black box models. They're so complex and sophisticated, a human actually can't look inside them to see how they've made their decisions. One way of getting around this is to use what's called a post hoc explanation mechanism, which is a mechanism that's external to the predictive model. So you apply it to the black box model, and it will attempt to explain the decision making of the black box model. Now, as I've said, this explanation mechanism, this interpretation mechanism, is external to the predictive model. So it's not inherent to the predictive model, it's an external mechanism that's trying to interpret something that we cannot understand. So then how do we know that the explanation mimics the decision-making of this black box model well? And that's quite a big challenge at the moment in the field of explainable AI. So there are a few different ways of going about this, but the problem that we found when we started was that many of these methods tend to be specific to a particular explainable method or a particular class of explainable methods, and so not comparable across different methods. And we also found that some of the methods that are, used that are comparable don't apply to tabular data, which is super important because the main data source for predictive process analytics is event logs, in other words, data in table format. So we needed to figure out some way to maybe adapt some of those methods to either be comparable or to apply to tabular data. And the approach we chose was to take an approach that's used in image and text mining, which is ablation based. So essentially what they would do is pick the features that are highlighted as the most important by the explainable method, and then remove them from a single input, and then predict again with this new altered input to see how much the model's output changes. So there's a couple of issues with this when we start trying to adapt this to tabular data. And one of those problems is basically that the changes becomes less absolute when you're working with tabular data. If you're working with a paragraph of text, for example, and your explanation says this particular sentence is the most relevant in this paragraph, then you can just delete the sentence. But in tabular data, when you try to take out a value from a row or from a column, then the predictive model will automatically try to substitute something in. So we had to pick something. We couldn't remove the features. We had to change the features instead, what we call the perturbation approach. And also changes are less, as I said, absolute. So we can't just, to put it simply, a change from 0 to 1 is a much smaller change than a change from 0 to 999, for example. So we had to figure out how to deal with that as well. There were sort of two main contributions from our work here. So one was developing this method of feature removal or perturbation in tabular data based on the explanation. And the second was applying this method then to a predictive process analytics problem to see how well two very well-known and popular explainable methods performed in this context. So as I said, we chose a perturbation-based method where we identified the most important features in the data from the explanation, and we also looked at the model output for the original input. Then using the explanation, we altered the features, again, based on the explanations. Often they would say, this is the range that contributed to this output. So then we would change it to something that was not within that range, and then predict it again with the new altered input. We did this 10 times and then used the mean absolute percentage error on the differences between the original and the altered inputs to try and see how much the model's output changed by. What we found actually was that the Fidelity results actually were quite small. So if you can see this table on the right here, you can see that the changes were actually quite small. We very rarely went past 0.5, which really meant we rarely got more than about half of the prediction probability. The degree of the change, sorry, was very rarely went past half of the original prediction probability. So we found that the results were quite small, and that stumped us a little bit. So does this mean that these two popular and well-known methods, which are actually well-known and well-respected in the field of explainable AI, did that mean they just weren't suitable for this context? And the answer we came up with was that's probably not the case here. There could be quite a number of different things that's causing this. You can see from our results here, the low results aren't particular to a particular data set or to a particular way of processing that data set before it was put into the prediction model. So then what was causing it? Well, there are quite a few things that could have caused it, and we looked into that a little bit further. When we were altering the features, we were altering the processed inputs. So when we're using event log data to make it readable to a prediction model, we go through these phases of bucketing and encoding, and that transforms each case into basically a row on a table. So it doesn't really capture that sort of relationship between events and their attributes. So when we were doing the perturbation, we were doing that on the processed data rather than the original sort of case. So we were only perturbing maybe just the attribute or just the event, not everything associated with that event. So that could have caused some issues. It could also be that the mechanisms of LIME and SHAP just couldn't identify those sort of dependencies between features, so between events and attributes after they were processed. And it could also have something to do with the underlying predictive model we were using. We were using the same in all experiments. So if it was something to do with the characteristic of that particular predictive model, that could have had some kind of effect. So then we thought about, where can we go from here? And we decided there was really three main parts we needed to take. So firstly, we thought, this perturbation-based method, we took it from or we adapted it from text and image-based methods, or methods that are used in text mining and image-based predictions. And as I said, the changes are a lot less absolute. So maybe it had something to do with our perturbation method. It could be that, the changes weren't big enough to justify or the changes weren't big enough to actually cause a major impact. But as I said, some of this was based on the explanation. So then that goes back to the method of perturbation based on the explanation. It could have something to do with the explainable method, maybe not identifying dependencies correctly. We also wanted to reevaluate some of the assumptions we made when we were developing this method. So again, we tried to change it to something that was outside of what the explanation said was relevant. So maybe if we had changed it to something within that range, maybe we would be seeing different results. That would be maybe a different type of fidelity. And we also dived into this, straight into this.
Excuse me for interrupting. May I remind you of the time, please?
Oh, I'm so sorry.
You're right.
So how long do I have left?
Well, the time is run out really, but if you could just wrap it up, so we have maybe time for one question.
Yes, my apologies. So in that case, I will leave it there. If you guys would like to know more about where we went from there, I will just kind of point you to that hyperlink in the bottom right corner. Thank you.
Thanks very much, Mythreyi. I think that was a wonderful presentation. Are there any questions? We have maybe a brief period of time for one or two questions.
We are in 11:15, huh? So in the other rooms, they started to move, I think, to the next presentation. So maybe one question, otherwise they can ask by chat.
Okay. So that doesn't seem to be the case. Then maybe if you have questions later, you can either come back or ask them in the chat. And we'll just move on to the second presentation. So thanks again. The second presentation is on the topic of requirements elicitation for applications running on a blockchain, preliminary results. So our presenter is Sarah, is that correct?
Exactly. Hi.
Hi. Please, the floor is yours.
All right. Let me
What happens, Sarah? We have lost Sarah.
Okay, so maybe just change the order. I can present now.
Yes, please. Yes, please. Yeah. We have to be
Okay,
agile because otherwise it will not
yeah.
work.
That's a
Thank
good
you.
idea. Yeah. So we do the demo.
Thanks, Chun.
Yes.
Yeah. So I start sharing my screen. Do you see everything?
Yes.
Can you see it? Okay. So I'm Stefan from University of Koblenz-Landau, and with us in the room there's also Nico. And if in our research practically we've built some tool for Camunda, which is a workflow engine. And our tool is able to find the best classifier for predictive process monitoring. And as you can see over here, this is the process overview in Camunda, in the Camunda cockpit. And for example, you have an instance over here. There is some instance running. Maybe it's a hospital and there is a process. The patient is a process, for example, and you want to find out the best method to be applied next. We can predict which one might be the best. And we also have different models which also can predict, like, for example, time. And you also see these models behave differently. So this random forest classifier returns slightly other probabilities for the next task and this n-grams, for example. And this is absolutely no problem because it's in the nature of these classification methods and also depends on the model. So, and maybe I quickly show you where to train and create these models. We have a tab over here, and as you can see, we have implemented some classification methods. For example, this n-grams classifier, which comes from text processing and is really fast and agile, but we also have some neural network classifiers. And you can see there are quite a range of parameters you can set. And yeah, imagine you are a doctor and you have no idea of machine learning, and now your boss told you, yeah, make this predictive process monitoring work in the hospital. You have to find the best classifier and the best configuration, and yeah, it all belongs to the model, and you have no idea how to do it. So for this case, we have built a tool for hyperparameter optimization. And you can see over here, there are all these classifiers. You can select a classifier. Okay, let's first name this test. It's a hyperparameter test. And for example, you want to check out this one and maybe also this random forest classifier. Yeah, you see there are these parameters and there are some meaningful ranges for these parameters to test. And you also see for this random forest, there are quite a lot of parameters. And if you can calculate cross product and stuff, it will have a very large configuration space to check. And if we will check all these configurations, it will take a long time. So yeah, this is basically what a grid search does. So we investigated about some hyperparameter optimization methods, and there are also some ways, for example, a random optimizer, where we randomly pick some configurations, or Bayesian optimizer, where we train a model which will predict the best combination. We all do this on a metric, for example, accuracy. And yeah, let's take this random optimizer on accuracy and start our test. Now it will search for the best classification method for this model, exactly for this model and exactly for the logs of this model. You see over here, I've already started some tests. So this is a grid grid search for this random forest, and you see there are 1,300 tested configurations, and there is also some with a Bayesian model, so it's just 10 configurations. And you see the accuracy of the best classifier doesn't differ a lot. So it does not make a large difference. And if you have not the time to test everything, it might be faster to use this Bayesian optimizer. And you also see our hyper test with a random search just finished. We have 26 tested configurations, and for example, a random forest with this accuracy, we just can random forest create. It is all persisted, the configuration. Can create it, and it's very smooth. We just can go back to, oh no, we have to set it visible, sorry. Yeah, we can just go back to our process overview to this point with a decision. And you see there is this newly found best classifier. And yeah, this is the prediction it does. Yeah, 97% for this task and 3% for this one. Yeah, so this is a quick overview. Are there any questions? You can just unmute yourself. I think it would be faster than writing in the chat.
Yes, you can ask your questions directly. Stefan finished in time, so please use the remaining time for asking questions. Otherwise, I will start maybe. Stefan, could you please remind to the audience, because everybody did not necessarily have the time to read the paper, the objective, the target of this tool? The objective of your research, the objective of your research, yeah.
Yeah, our research is based on another paper from Francesco Marino, and which is about the best classifiers. And our research was more practical oriented. We wanted just to find the best hyperparameter optimization methods, which are state of the art, and we found these to be the best ones. And our aim was to bring this hyperparameter optimization current state of the art into industry, so that there's really some tool you can use in place where you also have your models. So there are tools like Nirdisati where you can do the same, but you always have to extract your log, and you have to find the best classifier and then put the best classifier back again into your workflow engine. But in real, in a company, you do not want to have this transfer all the time. You just want to have all in one place and find your classifier fast. Yeah. So this was our aim for this tool.
Okay, thank you. Questions?
I can show you here for the Bayesian optimizer, for example, you also can select another classifier. Yeah. For example, you can take a regression to find the best hyperparameters, or random forest, iterative Bayes clustering. It's very slow. I wouldn't recommend it. Yeah. And all the error metrics, which are commonly used.
I quickly read in your paper this morning that one of your aims is to handle the storage problems, like as redundancy. But redundancy is not necessarily a problem if there are not conflicting data. Did you have some experiments with your tool that the problems that you have identified are solved, the redundancy problems and conflicting data problems with your approach?
Actually, I'm not quite sure if this is our paper, because in the program there's some wrong abstract for our paper, I think, and
not in the program. I read in the paper. No?
In the paper.
In the paper, but if you think that there is a mistake, maybe we should talk afterwards in order to correct the mistake.
Yeah, maybe we should talk afterwards.
But I read in the paper. Okay.
Yeah. Let's talk afterwards, because I don't understand the question about this redundancy at the moment. But the thing is, we persist some classifiers while this hyperparameter search is running, and we delete all the classifiers that we do not need anymore. So it's also very memory efficient, and we wouldn't store any classifier which is not necessarily needed anymore. We just store the 3 best classifiers in this case.
Okay, Stefan, thank you for the presentation in time. So we will move to Sarah, if she can share now her screen.
Yeah, I'll try. My apologies.
Let's go.
Yeah. All right. Can you see my screen?
Yes.
Yes, looks good.
All right, great. Sorry about that. So hello everyone, my name is Sarah. I'm from the University of Namur, and today I'm going to present you our paper entitled Requirement Elicitation for Applications Running on a Blockchain, Preliminary Results. So first of all, what's a blockchain? Blockchain can be defined as a distributed ledger that is structured into a linked list of blocks, and each block contains an ordered set of transactions. Ethereum was launched in 2015 and has now become the world's leading programmable blockchain. So, drawing on Bitcoin, Ethereum has offered a platform for anyone to write smart contracts and decentralized applications, or DApps, or dApps for short. What's a DApp? Well, at a minimum, a DApp is a smart contract and a web user interface. And despite their growing popularity, little attention has been paid to the software engineering aspect of DApps. Therefore, the goal of this work was to propose a preliminary list of DApp requirements. So we aimed to first elicit recurring user requirements of DApps, and 2, propose an early classification of these requirements. Collecting and analyzing requirements from a large group of users or future users has been a topic of interest in the literature. And one way to conduct requirements elicitation from the crowd is to use the app reviews. So we extracted the top 500 Ethereum DApps, and for each DApp, we recorded its name, its category, and its reviews, if any. And before we go further, we should note that many DApps belong to the finance, games, and exchanges categories, and that many DApps were not reviewed at all. So then we went on with the data annotation. So how did we handle that? First, we labeled each review with features and their associated sentiments. So for instance, we recorded terms such as easy setup, or statements such as there are not many cryptocurrencies. Afterwards, we grouped these terms and statements into more traditional requirements and properties. Then we classified these requirements into functional, non-functional requirements, and DApp properties. And finally, for each requirement, we indicated whether it was bound to a specific or a particular category, or if it was category agnostic. And the tables you see here summarize the results. and they showed that the NFR are basically similar to the ones relevant for centralized applications, and that DApp users seem to prioritize NFR such as user friendliness, documented, and user experience. Also, the functional requirements are distributed into requirements specific to the blockchain realm, such as support various cryptocurrencies, while others can be found in centralized applications as well. So, for instance, tag articles. And finally, we identified two DApp properties, namely the DApp should embody an interesting idea and an interesting concept and be transparent. So what are the practical implications of this? They are twofold. Firstly, the results can guide DApp designers in identifying the relevant requirements. And secondly, this requirement structure can be a stepping stone to advances, in blockchain-oriented software engineering. Obviously, these are only preliminary results, so this work definitely suffers from three main limitations. So first of all, we focused on requirement solicitation based on the user opinions. So this results in requirements from a user perspective. It's definitely super important, but in order to provide a more comprehensive framework, we should investigate other sources of data. Secondly, we were able to extract only a small amount of reviews. So this leads to results that are less robust than we would have liked. And finally, we deliberately restricted our analysis to Ethereum. Well, while we believe that the results will not change dramatically when expanding to other platforms, it would still be interesting to do so. Okay, so given the immutability property of the blockchain and by extension of DApps, the process of software engineering needs to be carried out carefully. Consequently, this work aims to be one of the first steps in that direction. And future works will consist in addressing the limitations I've just mentioned. Thank you very much for your attention.
Thank you, Sarah, for this quick presentation. So questions from the audience?
So Sarah, you said the non-functional requirements are pretty much very similar to traditional applications, right? Was there anything that really stood out for this particular domain of application?
For non-functional requirements, not so much. But I believe it's also because we have a long list of non-functional requirements for centralized applications. So it would be surprising to find something really specific to DApps. And the differences were more obvious for the functional requirements, actually.
So your argument or your observation in the beginning of the work is that classical usual requirements engineering methods are not appropriate for this kind of distributed applications.
Right. At least we should investigate whether or not they are applicable to decentralized applications. Because I think the question is fair. It's legit to see whether or not there are particular particular activities or particular processes that we should apply to DApps. But there are some works in the literature that highlight the need for blockchain-oriented software engineering. So it's been investigated, and you know, one of the particularity of decentralized applications is the fact that they are immutable. You know, once it's on the blockchain, you can't really change that. And I think it's a shift in paradigm compared to centralized applications, where we are kind of in agile philosophy, and we try to improve those applications in time. And with blockchain, it is kind of it's kind of different from what we have known so far.
In the first version of the paper, it was called decentralized applications, distributed applications, I think. And then it became blockchain. So why? Because there are also distributed applications which are not necessarily based on blockchains. So what is your position with respect to the needs of specific requirements engineering methods?
It is for decentralized applications. And when I say decentralized application, I mean applications running on a blockchain. So based on smart contracts running on a Ethereum or another programmable blockchain. Yeah.
Okay. I'm sorry if there are no more, because we are a little bit late. We have 5 minutes of delay, but we catched well finally the initial delay. So I would like to suggest to all of you to move. We are in room 3 here, to move to room 1, and then after to room 2. Okay, in order to regulate the circulation, if you wish. Otherwise, if you want to do in another way, you are free. Okay. So, and if you have questions, please send the questions to the authors through WOVA and open discussions. Feel free to do that.